Hi guys, Shouvik here. Welcome back to YouTube channel. So today we will solve another question from Leetcode itself. So let's get started. Yes, so today we have these problems, largest color value in a directed graph. Yes, this problem tagged as an hard and I feel so it's kind of indeed and hard problems for sure. Because here like on top rated topics that is generally most asked topics in any top product company's interview perspective, that particular topics we just need to incorporate to solve this. So it's an indeed and hard problem for sure. Yeah, so first we will understand the problem statement. So they have given a directed graph. So I guess you guys know some basics terminologies of graphs. So what is a directed graphs? What are undirected graphs? These things you should be aware of. So directed graphs is very simple. So for undirected graphs, if 0 and 1, let's suppose node 0 and node 1 is connected. So if you can go from node 0 to 1, so you can also from 1 to 0 also there is a path. So that is for undirected graph. But for directed graph, if the path is mentioned is source point from 0 and end point is 1, then from 0 to 1 you can only move. From 1 to 0, like backward movements, you are not allowed to do so. So that is the like very general definitions of directed and undirected graphs. So on these problems they have given us a directed graphs with n colored nodes and m edges. Right, the nodes are numbered from 0 to n minus 1. Very straightforward. And you are given a string colors where color psi is a lowercase English letter representing the color of the ith node. Simple, very simple. In this graph, 0 indexed. In this graph, that is of 0 indexed. You are also given a 2D array edges where edges j is aj indicates there is a directed edge from node aj to node bj. Also very straightforward. No super English they have written. They have written very straightforward, very understanding things only. A valid path in the graph is a sequence of nodes x1, x2, x3, xk such that there is a directed edge from xi to xi plus 1 for every 1 to I. 1 I and k, so I belongs to 1 to k. The color value, it is also like understandable. So they are basically looking from a path starting from node x1 and ending at node xk, and now they are basically defining a color value. So what is the color value? The color value of the path is the number of nodes that are colored with most frequently occurring colors along the path. So the color value is nothing but, if we are considering a node, if we are considering a path from let's suppose 0 to 4, like 0, 2, 3, 4, this path, then which color is most occurred? Which color is most occurred? So here you can see this A color, which is colored as red in this picture. So this color has occurred most times. So what is its most occurrence? It's thrice. It's thrice. So that's the reasons we have returned the colors as 3. So that's the reasons we have returned the color as 3. So now we have to return the largest color value of any valid paths in the given graph, or -1 if the graph contains a cycle. So we have to return -1 if the graph contains a cycle altogether. So I think there is like simple English they have written, and if you solve kind of, and if you have like basic understanding of graph, then understanding on problem statement, there should not be any issue. But if there is, so please do in the comments. I will maybe like take a note and try to answer those accordingly. So yeah, like let's go to some example test case so that you can get a more strong grip on the problem statement if you are not able to understand on any part of the problem statement. So in this case, you can see like A, B, A, C, A, that is the color of the node. So these are basically zero indexed based. So that means on 0 indexed we have colored 0. So that means node 0, we have node from 0 to n minus 1. So this means node 0 is colored with color A. 0, 1, node 2 is colored with color A. At node 0, 1, 2, 3, 4. And node 4 has colored with colored A. So here you can see in this example, node 0, 2 and 4 has same color, which they have highlighted as in red, which is nothing but color A only. And node B, which node 2 and node 3 are colored at different colors. One is in color B and another one is in color C. So they have mentioned node 1 has a color kind of like purple, and node 3 has a color is kind of sky blue. Yes, and they have given the edges. 0 to 1 there is a directed edge, 0 to 2 there is a directed edge, 2 to 3 there is a directed edge, and from 3 to 4 there is a directed edge. And we have already discussed, no? So from 0 to 3, 4, if we consider this path, then we are going to get the longest frequently occurred color. And what is this? This is color A. So, and it is colored as red here. So we are returning 3 here. So that is the largest, most frequent colors on a path of this graph you have found. On example 2, you can see. So there is only single node and the path is like itself altogether. So that means there is a cycle. There is a cycle, and they have clearly mentioned if the graph contains a cycle, if the graph contains at least one cycle. So we don't have to compute anything further. We can return -1 from then and there itself. Yes. And on constant, you can see n is colors length, m is edges length, 1 to our n can big as 10 raised to the power 5, m can big as 10 raised to the power 5, and colors consists of lowercase English letter, and these things like ai, aj, bj is within, like from 0 to n only, like 0 to n minus, right? Yes, I think the problem statement is very straightforward, and there is no super super understanding we need to understand the problem statement. Now we can quickly jump on the intuitions building part, which is the most important here. So on intuitions, like let's divide the problem. So whenever you found any graph problems, and you have the opportunity to divide it in some kind of sub problems, then do it. And also like that I am repeatedly mentioning to you guys, like for any graph problems, do the following things. Like if you are not able to understand any part of this, so please try to draw some demo graph, so that is must, you have to do. So that is bound, like you draw some demo graph of your pen and paper, and you can try to build the intuitions from that. And second is if there is an opportunity of solving some part independently, then do it for sure, because that is boiling down your complexity of the entire problems, So the first things, if we have an opportunity. So one is like, if you are not able to understand the problem statement, then you should have to follow the statement 1. But for our case, like let's consider we have understand the problem statement very deeply. So now we can jump on the statement 2. Do we have any opportunity to solve any part of the problems, which is basically help us to solve to only one particular directions. So if we have any part to solve it like independently, like that part, so we can solve it very independently, like that is, there is no dependency. And if we come like solve that particular part independently, then our one is the sub part of the question is solved. Do we have anything? Yes. So these things, or -1 if the graph contains a cycle. So this we can definitely solve prior, like for the cases. Now if we can go to our OneNote, so we have an opportunity. The opportunity is we have cases for which answer is not possible. And what is the case? The case is detect cycle in a directed graph. I guess you guys should know these basics, like detect cycle in a directed graph. But if you don't know, then I will definitely going to explain this, and I will also share my template on this video itself. So how you can detect a cycle in a directed graph. So for this I will be going to use like DFS only. So I will be going to use DFS only to detect cycle in a directed graph. So there are topics like you have solved, maybe you have solved like cycle detections in an undirected graph, but that is kind of is going to not work, because for directed graph there is some cases. So let's suppose this is the node structure, no? So let's suppose this is our node structure. So if it is an undirected graph, if this is an undirected graph, then you can consider this as a cycle. But if as it is a directed graph, so here you can see this to this, but it is not completed. Then again like this to this. So it is not a cycle. So your like visited or parent visited is not going to work for a directed graph. So for this we have a very known template, that is of path visited concept. What is the concept we have to use? Path visited along with normal DFS. So that we have to use here. So how it is basically working? So let's consider a graph. Let's consider any arbitrary graph. If I can number it, is kind of like 0, it's 0, then 1, 2, 3, 4. Let's say it's something like this, and this is 3, then 4, then 5, then let's suppose 6 is there, and let's suppose this is this, there is a cycle exists, and let me consider another case where there is no cycle altogether. So let's consider this only. So let's suppose we have this graph. No. So for this what we can do, we will do a standard BFS. We will do a standard DFS with a visited array, and a path visited array. So this path visited things actually helping us. So let me just now do some dry run. So when we are at node 0, so we will initialize our, how many nodes we have from 0 to 6, 0 0 1 2 3 4 5 and 6. And similarly so let's suppose, so this is our visited array, and similarly we have a path visited array for sure. So that is our path visited array. And all initially marked as unvisited. All are initially marked as unvisited, both in visited and path visited array. Yes. And this row actually for index. This row is actually for node or index, you can say. Yes. So now what we can do, we can start our DFS from node 0. We can start our DFS to node 0, and we will mark this. Both of them as visited and our path visited, both are visited. From 0 we can move to, which node we can move to? Let's suppose we have moved to 1. 1 is going to be marked to be, and from 1 we are going to move to 2. So we are going to mark 1 also as visited, and 1 is also going to be as path visited. And from 1 we are going to move to 2, mark both visited and path visited to be 1 and 1. Now from 2 we can move to node 4. Now mark both visited and path visited to 4. So this is going to be 1, and this is also going to be updated to 1, right? Now basically what we are doing, so for 4 we have no edges, no outgoing edges, which is not visited. So for 4 the DFS calls is going to be end, and it is going to backtrack. It is going to backtrack to 2. It is going to backtrack to node 2. Now for node 2, so now the point is actually node. So if it is unvisited, if it is a directed graph, then that is a cycle for sure. Which this is going to be a cycle. But here from this to this we have moved to this, but now we don't have any opportunity to move from 4. We are not able to move further. So the current path that we have explored there, from there when we are doing the backtracking, we are basically doing path visited to be unvisited, because we have considered that path. We have on the current path that we are in, the running current path of the DFS, the node is now not visited. Why not visited? Because we have backtracked from that node, but we already marked this as visited. So we are not going to encounter that. If we need to encounter that node again in via another path, then we are not going to do so, because it is already a visited. So for every node we are not exploring a node more than once, because we are following the visited array as it is. But for path visited, we are following the backtracking rules. When we are doing the backtracking, so that means the current path we are considering. So now till this from 0 to 1, from 1 to 2, 2 to 4, all the nodes that has marked in path visited as true is the current DFS cycle is currently on the DFS cycles path which we are visiting. And when we are doing the visitations, if we encountered a node in the current DFS flow which is already marked as a path visited also, then on that points we are very good to mark as a there is a cycle. So you will definitely get the gist when we are going to do this particular flow run. So let's move forward with the algo. So now from 4 we have done with the backtracking. So this is visited for sure. Visited we are not marking as unvisited, because otherwise there is going to be a multiple DFS calls for the same node, which is giving you a memory limit exit, like maximum recursion depth exists. So we are following very standard DFS template only for visited, but for path visited, as we are doing the backtracking, we are marking it as 0. So that means the current node is not on the DFS path altogether. You can explore it, but it has already explored. Including 4, there is no cycles altogether, so you don't need to explore. But including 4, there is no path exists which creating a cycle. So that actually the path visited holding. So path visited of 0 actually means it is not actually the current DFS cycle path, current DFS ongoing path. For this we have done the explorations, and we have backtracked from that node. Now we are at node 2. So from node 2 also we don't have any explorations pending. So we have done a backtracking. So when we are doing the backtracking, So for 1 also I am doing it on the same go. We are going to a backtrack for sure. So 2 and 1 are also on the same bucket. So we are marking for 2 also it is going to be path visited false, and for 1 also we are marking path visited as 0. So that means it is not on the path of the current path. Now from 1 we have another path. What is the path? We can go to this node 3. We can go to this node 3, right? Now we have landing at 3, and from 3 let's suppose we have go to node 5. So let's done this particular things, and from 3 let's suppose we are definitely going to move to node 6. So we are going to move 3 5 6. Let's do this. Let's do the DFS. Let's do the updations accordingly. So we are going to mark 3 as visited, and for 3 path visited as 1. Then we are going to 5, we are marking as visited and path visited to be 1, and we are going to 6 visited and path visited is also going to be 1, right? Now the game is actually going to start. Now from 6 you can move. Where you can move? You can move to 3. You can move to 3, right? And 3, and for 3, is it already visited? Yes, it's already visited. Is it also path visited? So that means we are in the node. We are here at node 6. So we are at node 6. So that means in node 6, the path that we have followed to reach node 6, we have just explored a new path. We have just explored a new path. So which is this? This is the new path. This is the new path. So we have explored a new path which is also landing me to a node which is also in my path visited. So that means the node 3 is also considered in the current DFS flow, is also considered as a current DFS flow. So that means there is bound to be a cycle for sure. So what is the cycle? So this is the cycle. So that's the reasons the node that we are now going to jump, so which is this transitions is actually landing me to a path visited node in the DFS flow, right? So now from 6, when we are going to check for 3, yes, it is a path visited. So that means if it is a path visited, then we have found our cycle. So return cycle found, or whatever the variables to be true. So there is a cycle for sure. So like this way this algo is basically working. So now I guess you guys is already aware of like standard DFS template, but if not, then I will just quickly show you my own template I have written to find the cycle detections with the same algo that we have discussed. But that is the high levels, the dry runs of the algo, how actually this is working. So now we can go to the code iterations of only the first part we have solved, guys. Only this part we have solved, where the graph contains a cycle and we have to return -1. So this is this part. So I think these things you guys is already aware, but if you not, so this is, I can quickly explain. So that this is actually the graph creation part. I have initialized my graph as a default dict of list, and so that is the adjacency list representations of the graph. And so how many nodes we have? So that is basically len of colors. So that means that many node we have. Now I have basically creating my adjacency list of graphs. So graph of U I have append to the node V. So that means there is a node from graph U to V. But if it is an undirected graph, then you have to write one more lines from graph V dot append U. So that means there is a node of backward from V to U. From V to U there is a node also. So but for our case it is a directed graph. Now we have initialized our visited to be from 0 to n and path visited from 0 to n, right? That we need. And now we have a function written is cycle exist, and how we are basically making the call to these functions. We are running for all the nodes for node in range n, and if the node is not visited, then we definitely have to make a DFS call. And from here we are making the calls of DFS. If that is not visited, then we are making a call of our DFS is cycle exist. So that is the standard DFS with the path visitations that we have just saw. We did it on these functions, and if these functions return me a true, then do we need to check anything further, or we are good to return a -1 for sure for this case? Then yes guys, yes, we are very good to return a -1 from then and there. So we are doing so. So we are returning a -1, standard straightforward -1s if there is a cycle exist. Now if there is, how we are checking this? We have mark visited of this particular node to 1, path visited to this particular node to 1 when we are first time landings to a node via DFS calls, and we are iterating to its neighbor. We are iterating to its neighbor for neighboring graph of node. If that node is not visited, then we are going to making a calls for its DFS calls of my neighbor. So here you can see I am making a calls to is cycle exist. So that is the DFS calls with the node as neighbor node. And if we have found there is a cycle exist, so this function is actually returning bool. So this function is actually return me a bool. So if my child functions calls, like call from the neighbor, found a cycles, then We are also good. We don't need to check further. From here also we can return a true. For this functions calls also we have done, because we have found a cycle in some child never call, in some child never call, so we can return a true. Elif, if that node is not visited, right? Sorry, if the node is visited, so the node that we are trying to jump, if that node is visited, then we are going to check if it is also a path visited. Oh, okay, that is our case. That is our case. Then we are returning a true. So that means the path that we are considering, they are via this path, the node which is already visited, and it is also lying to my path visited. So that is my DFL path, DFS path also it is lying. So that means there is a cyclic path exist in this graph, considering that particular node to the current node. Yes, that we have just saw in our one node, and we are returning true. And if this entire for loop executed and we are not able to find any cyclic path, then we are returning a false from here. But before that we are also have to unvisited the path visited node, unvisited the path visited node. So we are doing so we are basically doing the path visited node to be 0. So that means, so that it is not going to, we are not going to unvisited the visitations of it, but we are removing its path visitations, because this node is not a current DFS path altogether. This node is not a current DFS path altogether. Yes, agree guys? Yes, so that is the standard things we have returned to handle the -1 case. Now I think the major case is pending, which is we have to find the longest colored value. So now when we are, so after this entire executions like till line number 24, when if we are at line number 25, if our code is at line number 25, so that means we have some answer to calculate. So that means there is cycle altogether not exist. So we have to calculate the answer. So that is the part for this. So this is the part for this. So now we can quickly discuss the intuitions first, then we will discuss the code iterations, but let's first quickly discuss the intuitions. How now we can calculate the actual case. So I am giving you a very simple graph. Like we will build our intuitions actually how DFS is work, how actually the DFS is work. So from there you will see that how we are going to build our intuitions. So now you know a node should be colored in between how many colors we have. We have colored from A B C D like this. We have colored only A to Z, like it is of colors are consist of lowercase English letters. So from small a to small z we have colors defined. From small a to small z we have colors defined. So every node should bound to color with some color from A to Z, from some color to A to Z. Now we are going to see what is the extreme smallest graph is possible. So let's suppose we have a graph with only node 0, and let's suppose it has colored as a node colored as a colored A. So what is the answer for this? Is it 1? So the answer for this is 1. Yes. Now let's consider there is an edge from 1 to 0, and this is also colored as see guys, like that is the intuitions building. So please focus on this part like very deeply. So here actually we will build our intuitions from very small test cases, from very small graph to some very complex graph. So that is the sub problems we are trying to solve. If we are able to solve this, then we are create this generic logic to solve any problems of the world. So now let's suppose it has a connected component from 1 to 0, So for 1, now tell me guys, what is the answer? The answer is 2. Because on this path both are colored with same color of A only. So that is the most frequent color. Right? Now let's consider there is another edge of 2, and let's suppose this is also colored with colored A. On this case answer is 3. If now consider this is rather than A, it's colored with color B. Yes. Then on that case our answer is 2, because we have only these A's are colored as A. Now let's suppose this color is colored as not A, let's suppose Z. Now on that case our answer becomes 1, because this has colored as B, this has colored as A, and this has colored as Z. So the most frequent color that we have at is kind of all of them, and everyone's contributions is single only one. So that's the reasons we have returning 1 to the answer. So from this, so now let's make it like, so this is a kind of linked list. Now let's make it a little bit complex. Now let's suppose from 2, let's suppose we have one more edges that is of 3, and it has colored, let's suppose as color B. Yes. And let's suppose from 3 we have one more edges, let's suppose 7, and it has also colored as color B. Yes. So now how you can store this value, how you can store the value, what is the for node, for a particular node. Now the problem is for a particular node, we need to store what is the contributions, yes, what is the contribution, that is the intuitions, guys, focus on this. What is the contributions for every colors, right? And we know our colors are in range of small a to small z. So that is the range of our color. So now for every node, so for this node here, so for node 2, we have a path which is basically holding a1s, z1s, and we have a path where it is holding d thrice. So now for every node it can have multiple paths such paths. So here we have saw two paths. One is like this path, and another one is like this path, right? So we have saw two paths. So for this node, now we have to store for every path. So there can be, let's suppose, a path like this also, path can be this also, no? So there can be multiple paths, and for every path we just want what is the contributions of that path to my answer. What is the contributions of that path? Now we are looking for every path starting from current node, what is the contribution for all colors, So now I think you guys are getting the gist. So what actually the data structure should we look like to store these informations, so it is nothing but it should be, so let's suppose we have an arbitrary node as named as node. So for this node we have to store a list having a b c d till this, like this, till z, or it can store the ordinal value of this 0 1 1 2 3 like this till 25, 0 to 25, all the ordinal value of a to z. It is storing what is the contributions. So it is storing how many times a has occurred, what is the maximum on any path. So for a particular node, we have, see, there can be multiple path, no, there can be multiple path, and we are looking for on any path, out of them any path, what is the maximum count of a. Similarly, what is the maximum count of b, like this, what is the maximum count of till this z, till this small z, what is the maximum count of all of them. So if we are able to store these informations to a particular kind of DP table, so how my DP should be looks like. So my DP is kind of a list of list, or you can say like it is holding. So this is of size of 26, so that is of node 0, what is the colors it is holding. Then it will going to hold again a size of 26, what is the node contributions of node 1, like this, what is the contributions of node this. So like this we have total of tell me guys, we have total of n nodes. So that is the nth node contributions. So if we are able to store these informations for a particular node, what is the maximum contributions of every colors, so can I say my answer is ready? Yes. So that is nothing but the maximum of any of my DP tables value, any of the maximum value of the DP tables we can return. So that means from that node there is a path exists. From that node I am writing it also. So this actually mean from that node there is a path exist. Right? There is a path exist which holding the maximum occurrence of colored, let's suppose colored only. So our color can be from A to Z. So any of them. So what is the maximum occurrence of that particular color from node to all of its path, from that node to all of its path, if we are able to solve that informations to that particular DP tables. Now we are definitely sure that our job should be done. So for this we can do a standard DFS. We can do a standard DFS, how actually the high levels the algo should be looks like. So I am giving you a high runs kind of things, the high levels working principles of this algo. I will definitely do a code iterations also. So let's suppose for this particular node, as we are not able to explore any of further, so it is still 25. So let's suppose 2 has colored as colored A. So we are going to mark here this color has occurred 1 time, and when we are doing to backtrack, we are basically returning this list altogether to this node. And let's suppose this node is also colored as colored A, and this is also colored as colored A. So now it has found one of its child. So initially I have basically, when I am going to make a, before of making a never DFS call, never node DFS calls, I have created a 26 lens these things like colors of every nodes, the colors, the current list. So that basically holding the same information. So what from the current node, what is the contributions for every color? So initialized with 0. So that means for this particular node. So what I am actually trying to mean. So when you are basically trying for neighbor in graph of node, and your node is basically node 1 and your neighbor is basically 2. So if you are bound to check if my visited of neighbor is equals to 0, then you are going to make a helper calls or your BFS call or for your DFS calls with neighbor, and your neighbor is actually return you a list. You have stored it in LL. Now you have to process some things. So what is the processing? So your neighbor basically giving you. So for this on it has an occurrence of color A only once, that we have just, so others are 0 for our use case, right? So we are basically doing 26 iterations for I in range 26, and we are basically going to maximize, because what we are looking for my current node, what is the maximum contributions of all the colors from A to Z. How we are going to update? So I will going to update my current of I, because current of I is actually holding that information. My current of I is nothing but my max of what is the value my current of I is actually holding to what is the LL of I is giving me. I am taking the maximum of those. Like this way, my current of I is going to be updated with the all of its child, all of its path. What is the maximum value it is holding? What is the maximum value of that particular color it is holding? Yes, agree guys? Yes. And there is one more case. If let's suppose it is visited. So if it is land down to else case. So if it is visited, so that means its DP is already calculated. Yes, right. So that means its explorations already done, and we have already stored its child, its neighbor actually. So our LL is actually coming from our neighbor only, no? So we have already calculated the maximum contributions, the LL actually for its neighbor. So we are basically directly making a call or to calculate our LL. So our LL, we are not making a functions call, we are checking our DP tables. What is the value of DP of neighbor? Can you give me the list? And we are doing the same things for I in range. Tell me guys. 26, and my current of I is nothing but max of my current of I and my LL of I. Yes, that is the contributions. Yes, and before returning from the functions, the helper functions or the DFS functions you are following, you must have to store this. Particular value, so that it is not going to recalculate again. That is the DP we are using. So DP of node, we are storing the current. So now are we good? I guess we have missed one more case, because we have not considered the current node contributions. So let's do it. So the current node contributions, we have taking the ordinal value of what is they have given to us. I guess they have given to us colors. We have given to us the colors, right? So we are going to take where we are. Yes, we are here. So we are going to take ordinal of, okay, it stopped working. Wait for the program to restart. So it's, and yeah, can we write now? Yes, we can. So we are basically doing colors of this particular node. So that is the ABCD values we are getting. We have done its ordinal, and we have minus 97 so that it can fit from 0 to 25 index, and we have definitely increased its contributions, that is of the current node color contributions, and then we are very good to store it. And finally we can return the current node, current list altogether. So that is the final list we are able to build standing at current node. So that is so this current is actually holding a, so this is actually, you guys is already aware, that is actually a list which is basically, it's every node is actually holding for A, B, C, like this till Z. What is the contributions? What is the maximum contributions of this particular color? Yes, that we have already saw. Now we can go to the code iterations for sure. Yes, so we are done till line number 24. So this part is only remaining. So we are going to do this. So similarly, the same things I have written here. So for node in range in, we are going to make a functions call if it is not visited. So for node in range in, if that node is not visited, so before that, please take a care, like visited of, you are basically make the things unvisited altogether, and you are basically making up, you like run your next DFS or helper functions, whatever you are preferred, you can run, because this visited we have already used in the previous method, no? So it's already updated. So create a new visited or redefined it. So you have done it, and if my visited of node is not, then we are making a helper calls that, and it is going to return a LL. It is going to return an LL, that is the list or the current node, or I can write it as it has returned a current that we are seeing. And we have already discussed that we have to consider what is the maximum contributions of entire DP tables. So can I do this in place? In place? So that is the optimizations we have added. So this particular current is actually giving me for current node what actually your list should be looks like. So when I have my list in hand, can I run a 26 iterations loop and update my answer to be max of answer to all of these values, to all of the values of my current? So that particular node, what is the maximum contributions of all the colors? I will taking the maximum of all of those. I am taking the maximum of all of those, right? And I am finally returning my answer. So now the pending thing is understanding of this helper functions. So the helper functions is very straightforward. You can see I have defined my visited, redefined. DP we definitely need. DP is a default dicta of list for sure. So my visited of node is I have marked this as 1, that we are standardly doing, and I have initialized my current to be 0 of 26, because initially none of those are visited. Because we none of those we have not considered. We have just initialized what my current should be, like my current list should be looks like. So initially I have initialized with all zeros. Now I am iterating for neighbor in graph of node. If my visited of neighbor is 0, I am making a helper call to my neighbor, and I am fetching the list. And when I have list in my hand, I am iterating to my list for I in range 26, and I am updating my current of I to be max of current of I and LL of I. And if that is not so, if that means it is already visited, then who is going to give us the answer? DP should be. We are calling our DP to be LL of DP of neighbor, and we are doing the same things. We have found our LL, and we are iterating to for I in range 26. Current of I should be maximum of itself and LL of I. And finally, what is the current node color contributions? It is nothing but current of order of colors of node minus 97. Yes, that's the ordinance we have done, and fit it to be 0 to 25 range, and we have increased the current node contributions to be plus equals to 1. Yes, and finally we are also storing to be the current list to be in my DP of node, and finally we are returning. Yes, so that is all about the entire code iterations and entire intuitions building for this particular problems. Now we can quickly discuss the time complexity for this. I know it is a hard problems for sure, and there are multiple topics in a single video you guys are learning, right? You have learned in a single video, you have learned cycle detections in a directed graph, DP on a graph, which is the most difficult topics of any interview perspective, and top product companies very likely to ask to this question for sure. So now we can quickly discuss the time complexity. So the time complexity is nothing but I am not going to every line's time complexity because it's already a complex. I am writing it kind of a like big only. I am writing it in kind of big only, and I am also suggest you like on interview, if this question is altogether asked, and if you are able to explain the problems and your solutions with this much clarity is more than sufficient. You can write your time complexity in bigger versions. You don't need to like every line's time complexity. You don't need to mentions, because graph creations like cycle detections, you don't need to write like every line's time complexity like this way. You can write it in kind of like big one. So the time complexity is big of v plus e. That is the standard time complexity of DFS. So we are running 2 DFS. It is kind of big of 2 plus v plus e, but there is a factor. There is a factor for sure, because we are for this DFS we are running a 26 length for loop also. So here also we are running a 26 for loop. So it is kind of like how many times we are going to run it. So we are going to run it one on this times, and another one is like this times, and it is not a one time. It is basically how many neighbors it can have for a particular node. So if I can consider a particular node has k neighbors, so this is going to run a k times, and k into 26 times, right? This can be as big as k into 26 times. So that many neighbors a particular node has, and for that we are hitting a 26 factor. So you can consider it is kind of a for every v there is a k factor. For every v there is a k factor, and our k factor is as big as like how much? K is nothing but 26 into maximum never of a node. Maximum never of a node. Yes, that only guys, that only. So it is kind of a big of v plus e, but explicitly mentioned this fact for sure, because that is the extra hit we are basically pushing to standard DFS. So it is a good to mention these things, and I am also feeling you should mention this is kind of like big of v cross k plus e. And on space complexity, tell me guys, what is the space complexity for this? Space complexity, I think so we are on very good note. You can directly mention in kind of big of v plus e only, because the storations of graph only is going to take the maximum space. That is a big of v plus e to store it in adjacency list configurations. And then we have like visited, DP, then path visited. These are also kind of big of in, and DP is kind of, yes, it is also a kind of like graph storations only, because this is also a default dict of list, which is going to take a big of v plus e space for sure. So you can write it in big O terms only, big of v plus e. That is the maximum space you are going to consider. Yes guys, so that all about these particular problems, like entire from intuitions building to entire code iterations, my template explanations, and finally we have completed the time and space complexity analysis. And if you guys are able to understand till this point, I am done my best to explain these particular problems. So please do subscribe to our channel, and please share the videos to your friends circle who are also preparing for top product based company and brushing up their DSS skills. And please turn on the notifications, so that when we are going to live to our next video, you are going to get the notification as soon as possible guys. So that's it guys, that's it for today. Let's meet tomorrow with another beautiful question. Bye guys, bye.